So in this video, we are going to continue what we have left before. In this part, we are going to continue with our last module. Okay. In this chapter, we will cover about the artificial neural network. So basically in this chapter, okay, we will cover all these subtopics. Okay, so okay, so we will learn about the term in artificial neurons. Okay, what is input? Okay, what is output? What is the weight? All right, and we will also learn the architecture of Mac-Callard-Pitts models and the architecture of Frank Rosenblatt model, layers of neural network, the activation function, and the perceptron learning. So these are terms that you have to be familiar with when we are learning neural network. Okay, these are terms that involve. Okay, you have the input signals, you have a set of real valued weights, an activation level, and also a threshold function. Okay, so for input signals, okay, we will have a set of data. Okay, a set of data that comes from any kind of form. Okay, it depends on your data set lah. Okay, the input signals. So different model, okay, will be different. Okay, and its allowable range of the input values will also different. Okay, it depends on the data sets. So typically inputs are discrete. Okay, discrete from the set of 0, 1 or -1 to 1 or real numbers. Okay, that is the input signals. And the second term is a set of real valued weight, or in a formula we use the symbol of WI. So the weights describe the connection strength of the network. And the third term is an activation level. This is what you include in the formula of your neural network, the activation level. Activation level we determine by the cumulative strength of its input signals. Okay, so we have a set of real weight, right? And then the activation level is the total. Okay, you add all the weights and then you will have the activation level. Okay, each input signals are scaled by the connection weight along with the input line. So the activation level computed by taking the sum of the weight inputs. Okay, total of the weight input. You add weight 1, weight 2, plus weight 3, plus weight 4. What is the total weight inputs? Okay, all right. And the fourth term is a threshold function, or F symbols. So the function computes the neuron's final or the output state. Okay, neuron final or output state by determining how far the neuron's activation level is below or above some threshold value. Below or above the threshold value. So the threshold function is intended to produce the on or off state of actual neurons. Okay, so that's the term in artificial neurons. Alright, now let's take a look at the figure 11.1 here. This figure is figure for the artificial neurons. Okay, so as we mentioned all the list of the terms in the previous slides, So we have the input vector here, x1, x2, x3, all the way until xn. We have the weight, okay, w1, w2, w3 until wn, and the total weight and the formula for the neuron. Okay, so there are many tasks that you can use using the neural network. Okay, these are some of it lah. Classification, pattern recognition, memory recall, prediction, optimization, or even noise filtering. Okay, so this is the architecture of artificial neural network. Okay, this are the architecture of neural network. So if you are given this figure, you should already know actually this is the architecture of neural network. Okay, so we will have 3 layers. We have input layer, middle layer, and output layer. And we have all the input signals coming to the input layers. And then we mix the input signals from the input layer at the middle layer, and then we have the output layer, and finally we will have the output signals. Okay, so how can we use artificial neural network to learn? Okay, learn, that's why we call machine learning. Okay, machine learning, the term machine learning itself have the word learn, right? So actually we are trying to teach the machine. We are trying to teach the machine to do some task based on the previous knowledge. Okay, so there are several kind of techniques to learn. Okay, we already cover in previous tutorial, right? Where we use case-based reasoning to do the prediction. Okay, that means we use the previous case to learn the new we use the previous cases to predict the new case prediction results. Okay, that means we use the previous case to as a learning materials. So same goes with this one. Okay, case-based reasoning kita ada all those cases. Okay, case 1, case 2, case 3. This one, what is the how many layers we have here? The inputs. Okay, that is what we learn. Okay, the input layers, that's what we learn. Okay, so the artificial neural network actually it learns by the neurons that connected by links, as you see here. Okay, let's see, this is the first input. You put the middle layer. See, you mix up all these inputs at the middle layer, right? So that's when the learning and connected by links that comes with the numerical weights. Okay, and the weights are basic means of the long-term memory in artificial neural networks. The weights normally express the strength, okay, on the other words of each neuron's input. Okay, a neural network learns through the repeated adjustment of this weight. Okay, you can adjust the weight. Okay, every time you adjust the weight, the output will be different, and that is the process of learning for the artificial neural networks. So, does the neural network knows how to adjust the weights? So, basically, the neurons that connected to the external environment form input and output layers. Okay, neuron that connected to the external environment will form the input and output layers. So the weights are modified. Okay, the weights are modified to bring the network input or output behavior into the line with that of the environment. Okay, to build the artificial neural network, we must decide first how many neurons are to be used and how the neurons are to be connected to form a network. Okay, so when you are given a case study, okay, a case study, and then when you have that case study, you have to decide, okay, how many neurons will be included. Okay, how these neurons will be connected. Because for every case study, you will have a different total of neuron. Let's say you have 4 different input, so that means you will have 4 neurons. Okay, so those neurons will be the input, and then input to the middle layer, and combined with the weights, you will have the output layer. So in other words, we must first choose the network architecture based on the actual artificial neural network architecture lah. Okay, then we decide which learning algorithms to use, and finally we train the neural network. That is, we initialize the weight. Okay, that's the first step. Okay, first you choose neural networks, and then choose the learning algorithm, and then initialize the weight of the network, and update the weight. Okay, 4 steps of 4 steps of training or learning in neural networks. Okay, so the neuron, as simple as computing element. So a neuron receives several signals from its input link. Receive signals, compute new activation levels, and send it as output signals. So these are the 3 rules of a neuron: receive signal, compute activation level, and send the output signals. Okay, so the input signals can be raw data or the outputs from the other neurons. That means this is one neuron. It can be connected with other neuron also. Okay, so this, if the data is directly come from the data set, that means it's a raw data. Okay, so the output signal can be either final solution to the problem or an input to other neuron, because these neurons can connect to other neurons, right? Okay, so these are the diagrams of the neuron lah. You have the input signals, the weights, the neurons that do all the learning process. You know, the neurons function as we have here. Okay, these neurons that receive signals, compute activation levels, and send the output signals. Okay, send the output signals. Okay, so how does the neuron determine its output? Okay, so back in 1943, Warren McCulloch and Walter Pitts proposed a very simple idea that is still the basis for most artificial neural networks. So the neuron computes the weighted sum of the input signal. The weighted sum, that means the total weight, and compare the results with the threshold value. So if the net input is less than threshold, so the output is 1. But if the net input is greater or equal to the threshold, the neuron becomes activated and its output attains a value plus 1. Okay? Alright. So this is the architecture of McCulloch-Pitts model back that they draw this model back in 1943. So you have list of inputs, right? Input 1, 2, all the way to input n, and weights, weight 1 all the way to weight n. Okay, the neuron, okay, the threshold value, and the output. Okay, so this is the formula. Okay, so if x is greater than, or if x is, okay, the total, okay, x is the total. X is the total of input times the weight. Okay, this times this. Okay, xi input w weight. Okay, then you will have the x. Okay, you total all this in a neuron. Okay, and then you already have the output value here, and then you will compare. Okay, so if x, this value x, greater than the threshold value here, okay, you add 1. If x less than the threshold, minus 1. So x is the net weighted input to the neuron, okay. Xi is the value of input, W is the weight, N is the number of neurons inputs, and Y is the output of the neurons. The weights mean it will be normalized. Okay, it will be normalized. The weights is between the range of 0 to 1 or minus 1 to 1. And the output will be in the term of binary. Okay, so but there are some disadvantages of this architecture. It's so simplific, that means very simple. It only generates binary output, and the weight and threshold values are fixed. Okay? Alright, continue. And then after that, we have the updated version of architecture. Okay? So this one is the previous one, the McCulloch and Pitts was created in 1943, right? So this is the architecture of Frank Rosenblatt's model. They created it in 1950. Okay, they're trying to improve the previous model. So for this architecture, you have the inputs and weights, but you have the, instead of comparing it with the threshold value, here you have the perceptron and the activation function. Okay, so here this model try to improve the McCulloch and Pitts by introduce the perceptron. Okay, for this model, they apply a Hebbian learning rule of adjusting the weight. Okay, they adjust the weight. The previous one didn't adjust the weight. Whatever the weight is, they just calculate it. This one, they adjust the weight. So the perceptron model added extra input, which is the bias. This one, bias. Bias is added to the total neuron calculation. Okay, so the first stage, the McCulloch and Pitts model only do the linear combination of inputs, right? They do the summation and just calculate the inputs and the weights together. And each input array is associated with weight value, normally between 0 and 1 after the normalization. Okay, and the second stage in this part where they pass the sum of product to perform activation function. They pass the sum of product to perform activation function, where this activation function will generate the outputs from the neuron. Okay, in the previous formula, you only have this part, right? Okay, only the total weight, total input times weight. But in this one, you have to add the bias. Okay, that's the difference. So, in neural networks architecture, you can have several layers. You can have single layer of neural network, you can have multi-layer of neural network, and you can have a competitive layers of neural networks. Okay, it depends on your data and it depends on your goals. So this is the example of the single neural networks architecture. Okay, single layer. Single layer means we only have one layer of weight. Okay, only one layer of weight. Okay, example you can see here. Okay, you have input. Okay, and then you have weight. Okay, and then you put everything. You have bias. You put everything in the neuron, and then you have the output. That is single layer network. Okay. So the perceptron. Okay, perceptron. So perceptron, what is perceptron actually? Perceptron is a single layer feed-forward network introduced by Rosenblatt. Okay, its training use Hebbian learning. Okay, this is the algorithm for perceptron. Okay, step 1, it has all the way until step 6. Step 1 for this algorithm, it will initialize all the weight. Okay, weight equal to 0 and the learning rate. Okay, it has the learning rates alpha in between 0 and 1. Okay, so step 2, while still not fully trained, okay, if the network haven't been fully trained, we do step 3, 4 and 5. Okay, so step 3 is for each training vector and target. Okay, for each training vector and target, we calculate the net input. Okay, we calculate the net input. Okay, so in this net input, we add bias plus the total of input times the weight. Okay, and the function. Okay, so if net is greater than 0, okay, it will be, output will be 1. If net equal to 0, the output will be 0. If net less than 0, the output will be minus 1. So, and then after that, we move to step 5. So, if output not equal to y, okay, if output not equal to y, so the new weight, okay, we will calculate the new weight. Okay, we update the weight. Okay, that's why we call as activation function. Okay, we update the weight, which is the old one plus the the um, the old one plus the learning rate here lah. The learning rate alpha is the learning rate, right? Okay, so and then after that we also, after we calculate new weight, we also calculate a new bias. A new bias which is the old bias plus the learning rate. Okay, and then once we done that, we move to the step 6, which is we test the stopping condition. Stopping condition here, this algorithm will stop once the output equal to 1. Okay, that's the perceptron algorithm. So, and this is the multi-layer neural network. So multi-layer neural network have 2 or more weight layer. It consists of an input layer 1 or more middle layer and an output layer. So you can see here, right? You have several input. You have first hidden layer, second hidden layer, and the output layer. Okay, as long as it's 2 or more layer, that is considered as the multi-layer networks. Okay, all right, so why is middle layer in multi-layer network we call it as hidden layer? Okay, why we call it hidden layer here? Okay, so what does it mean by hidden layer? Okay, hidden layer, that means it hides the desired output. The neurons in the hidden layer cannot be observed through the input-output behavior of the network. There is no obvious way to know what the desired output of the hidden layer should be. In other words, the desired output of the hidden layer is determined by the layer itself. Okay. Can neural network include more than 2 hidden layers? So normally in a commercial, in a big company, artificial neural network incorporate 3 and sometimes 4 layers, including 1 or 2 hidden layers. So each layer can contain from 10 to 1000 neurons. Okay, so the experimental neural network may have 5 or even 6 layers, including 3 or 4 hidden layers, and utilize millions of neurons. We're talking about huge data sets. Okay, you cannot run this kind of data, this kind of neural network on a regular computer. You need a server. Sometimes you need also a GPU to run this kind of layers. Okay, so most practical application use only 3 layers because each additional layer increase the computational burden. Okay, it's gonna be so huge and takes a lot of time. Okay, we cannot run it on a regular computer lah. Okay, so the competitive layer network. Okay, competitive layer network is where we close the loop networks. Okay, we close the loop networks. For example, we have A as the input here, so we close the network. Okay, we close it. It's just within that circle. Okay. And the activation function. So activation function usually don't use weighted sum directly. Okay, like the formula that a model that was proposed by the McCulloch and Peat. Okay, they just simply calculate the weighted sum. Okay, but for activation function, they don't normally do that. Okay, they apply some function to the weighted sum before it is used. Okay, that is what we call as the activation function. Okay, so the activation function is, there are several functions lah out there that you can use, the sigmoid function or linear function or the Gaussian function. Okay, so the basic structure of neural network here. So this, when you have this, we call it as a threshold. This one is linear. Okay, this one is Gaussian and this one is sigmoid function. Okay, different function. So for step function, okay, it depends. If the value of x is greater than or equal to 0, it will be 1. If x is less than 0, it will be 0. Okay. For the sine function, if x is greater than or equal to 0, y will be plus 1. If x is less than 0, y will be minus 1. For sigmoid function, okay, 1 over 1 plus the exponent of negative x. And for the linear function, simple lah. Okay, y equal to x. Alright? So these are some activation functions of a neuron that people use in a neural network. So, the sigmoid activation functions. Okay, the math of some neural nets required that the activation function to be continuously differentiable. Okay, look at the others, they don't really do the differentiable, right? Only the sigmoid function. So the sigmoid function is mathematically function having an S shape, the sigmoid curve, this curve. So this sigmoid function is, as we mentioned before, 1 over 1 plus e to the exponent of x minus x. Okay? So this is the example, sigmoid example. So let's say we have the input here. Okay, we have input of 3, 1, 0, and minus 2. And we have the weight here. The weight here is 0.3, minus 0.1, 2.1, minus 1.1. So, given this input, what will be the output? So, let's see at the calculation. Okay, first you calculate the x which is the input, right? So we calculate the input here times the weight, right? So 3 times 0.3. 1 times minus 0.1. 0 times 2.1. Minus 2 times minus 1.1. So you get the value of x is 3. Okay, so you put in the sigmoid function. So f3, okay, fx, right? f3 equal to 1 over 1 plus the exponent of negative 3. Okay, so you will get the answer for the sigmoid function is 0.953. And then for this one, okay, let's say we have the input 2, 10, 0, and 3. Okay, using the same weight here. Okay, so 2 times 0.3 plus 10 times minus 0.1 plus 0 times 2.1 plus 3 times minus 1.1, and then you will get minus 3.7. And you put the formula inside the sigmoid formula, 1 over 1 plus the exponent of minus 3.7, and then you will get 0.0241. Okay, so a two-weight layer. Okay, a two-weight layer in a feed-forward network. So if you see two weights, okay, an arrow is pointing to the next neuron. That's what we call as two weight layers. Feed forward. Feed forward is arrows is like this. Feed forward. Okay, feed forward network. So that means for this example we have two inputs, one output, and one hidden unit. This is the hidden unit. So you do the calculation. Let's say the input is 3 and 1, and the weight is 0.5 and minus 0.5. Using the sigmoid function here, what is the output? Okay, so the output will be, okay, so input 3 times the weight 0.5 plus input 1 times minus 0.5 equal to 1. Okay, and then so we put the x value 1 here. Okay, so in the formula 1 over 1 plus exponents of minus the x value, which is 1, and then we will get 0.7311. Okay, All right. And then for the hidden layer, okay, we substitute the value. So we calculate x2 using the fx1. We already have fx1, right? fx1 here, the value here 0.7311 from this formula, okay, times 0.75, right? Because we already have 0.5 given in the questions, right? Okay, times 0.75, and you have the output value 0.5483. Okay, now we already arrived here. So after that, what we have to do? We have to calculate again fx. This is just fx1. And now we have to calculate fx2 based on the new x value. Okay, we put this value in the formula again. 1 over 1 plus exponent of negative 0.5483, and then you will get 0.6337. Okay, that's the example for the what is it? Two weight layer feed forward network. Okay, we will have a lab next week about the perceptron, about calculations. Okay, so that is all for this video introduction about the neural network. Okay, I'll see you guys next week. Okay, thank you.